Okay, let's talk about confidence intervals. We've seen this before, so just a quick review of terminology. Remember, a parameter is a number used to describe a population, and a statistic is a number used to describe a sample. Statistics are from samples, populations are associated with parameter is a number associated with a population. Okay, so you can go by that initial letter. Okay, the confidence level represents how confident we are that a particular confidence interval contains the population parameter. Okay, and how do we get a confidence interval? We get it by starting with a point estimate from the parameter, which is going to be a statistic from the sample. And then we use that to create the confidence interval. If we perform that algorithm a whole bunch of times over a large number of samples, all the same size, and each of those samples gets us a separate point estimate of our parameter and a separate confidence interval. Some will be narrower, some will be wider, but if we're at a 95% confidence level, then about 95% of all of those confidence intervals should successfully capture the population parameter. Remember, your margin of error is your distance away from the point estimate on either side. So we take our point estimate and then we add and subtract the margin of error. Okay, so let's talk about the confidence interval for the population mean. Okay, so we've discussed this before. Remember, our point estimate for the population mean is going to be our sample mean, x bar. And so what we're going to do is we're going to start with x bar, and then we are going to add and subtract the margin of error. And the way we create the margin of error is we take our critical value of z, assuming that our sampling distribution follows a normal distribution, our multiplier, which is a critical value of z, multiplied by our standard error. And our standard error is the standard deviation of the set of all the possible sample means for that particular size sample. Okay. What's the problem here? There's a very important problem. How do we find the population standard deviation? Because to get the standard error, we need that. We need that sigma. To get the confidence interval. Okay. Okay, and our sigma of all the x bars is equal to our population standard deviation divided by our square root of n. However, what do we need in order to find the standard deviation? Do you remember how we calculate it? What we do is we take all the data points, and from each data point we subtract the population mean. Wait a minute. We don't know the population mean. So how in the heck are we going to find the population standard deviation? We can't do it. Okay. We can't calculate the standard deviation because we do not know the population mean. Okay, so we kind of have a problem here. So our really only option is to use the sample standard deviation as an estimate of the population standard deviation. However, it's generally not accurate because samples are more spread out than populations relative to their size. In other words, the sample standard deviation is going to be larger than the population standard deviation. Okay, so where do we go from here? Okay, So let's go back to our central limit theorem. Okay, from our central limit theorem, we know that our z-score of my z-score of my x bar is going to be normally distributed as long as my n is sufficiently large. And it turns out that a very common rule of thumb for that is that my n has to be at least 30. There are other rules of thumb, there's other guidelines, but that's a very commonly used one. Okay, but for small samples, that z-score is not going to be normally distributed. Okay, so where do we go from here? So we go to something called the student t-distribution. So why do we call it the student t-distribution? Back in the 1800s, early 1900s, there was a mathematician in Ireland, and he was a chemist, and he worked for a brewery in Ireland. And he did a lot of analysis for them, and he really concentrated on small sample sizes, and he found out that this quantity that we're talking about, which is x bar minus the population mean divided by the standard error, and notice in here that we are putting the sample mean in that denominator instead of the population. Sorry, let's make that the sample standard deviation in that denominator instead of the population standard deviation, because we do not know the population standard deviation, so we're using the value from the sample instead. He showed that that little quotient there did not follow a normal distribution, but instead followed a different distribution. This distribution eventually became known as the t-distribution. And the reason we call it the student t-distribution is because Gossett was prohibited by his brewery from publishing under his name, trade secrets and all. And so he got the brewery's permission to publish his results, but he had to use a pseudonym. And the pseudonym he chose was Student. And so he was known as Student, but of course it came out later, his real name. And he is revered as a very important contributor to the field of statistics. Okay, so what is the student's t-distribution? So here's a graph. If you'll see that in a way it looks kind of similar to the normal distribution in that it's at least somewhat bell-shaped, but it turns out it's not quite the normal distribution. Okay, so what happens with the t-distribution for small samples is that the tails are thicker. So, okay, so quick review here. Degrees of freedom. So the degrees of freedom abbreviated lowercase d lowercase f, that's going to be equal to the number of data points that are free to vary in the presence of a statistical estimate. In our case, the sample mean. For our purposes, where we are in this class, it is good enough to remember that the degrees of freedom is equal to n minus 1. That's good enough for our purposes. Okay, so whatever our sample size is, we subtract 1, that gives us the degrees of freedom. So if we look at this little picture here, and let me see if I can highlight here, the distribution with the lowest peak is the one with the smallest degrees of freedom. Let me just outline it a little bit. Okay, so what's the total area under any of these curves? 1. So if it's a lower peak in the middle, then what has to happen? It has to have fatter tails. Let me see if I can try to draw it at least a little bit. Okay, fatter tails. Okay, so that would be in this case, 2 degrees of freedom. Okay, so the normal distribution is going to be one that's highest in the middle, which means it has skinnier tails because the total area has to be 1. So if it's going to be higher in the middle, it's got to make up for it by being squeezed in closer to the x-axis out in the tails. Okay, so this would be our normal distribution. And so if you had higher degrees of freedom, it's going to be somewhere in between. So it's probably not that easy to read. I'm not going to try to draw another one because I don't think it would work well. Okay, so the t distribution has fatter tails, lower in the top. The larger your sample size, that's going to make your degrees of freedom larger. The larger your sample size and your degrees of freedom, the closer it gets to looking like the normal curve. Okay, so the higher up your degrees of freedom go, the more and more your t distribution starts to look like a normal distribution. And that's why people before Gossett didn't figure it out, because they were looking at large sample sizes all the time. But he started looking at small sample sizes and figuring out that it really mattered whether you use the sample standard deviation in that denominator or the population standard deviation. Okay, so the student's t distribution is what we're going to do here. And by the way, this figure came from the online statistics project at Rice University, and they have an online stat book which is open resource for anyone to look at, and it's actually an excellent resource if you ever want to look things up. Okay, so let's talk about the constructing the confidence interval for the mean. Okay, and you say, yes, we already did that in the other section, but that was, we had sort of a fake assumption there because we were saying that we knew the population standard deviation. In reality, we cannot know the population standard deviation unless we also know the population mean. Okay, especially for small samples. Big samples, it really doesn't make that much difference. Okay, so we're going to go basically back to the same procedure we did before. Alpha works the same way. 90% confidence level means that alpha is 0.1, and 95% confidence level means that alpha is 0.05. Half the alpha goes in each tail. We've done that before. Okay, here's the difference, is that this time, instead of talking about a critical value of z, we're talking about the critical value of t on that t distribution. Okay, so in order to do the t distribution, we are assuming that the variable that we're measuring is normally distributed in the underlying population. However, if it's not, you're generally still okay as long as your sample size is sufficiently large. And by sufficiently large, we generally mean that the n is at least 30. And if there are not many outliers. Okay, that's the key thing that we're looking at here. Okay, another little aside that we're not going to run into in our class, but it's important if you decide to do any real analysis later, is that if your sample takes up more than about 5% of your population, you have to multiply by a correction factor. And that's because if you have a real small population and you take one of them away and put in your sample, then that changes the probability of any of the others being chosen. I would not worry about that for now. So just kind of be aware that it's out there. Okay, so here's what we're going to do. Check that your assumptions are met. In other words, our population's got to be normal, or our sample size has got to be sufficiently large so that it's okay if it's not quite normal. N bigger than or equal to 30 is going to be the rule of thumb that we're going to use. Figure out our confidence level, which is really going to be 1 minus alpha. Or if you're given the confidence level, figure out your alpha. Figure out your degrees of freedom, n minus 1. Draw a little picture of the t distribution. You saw it look real similar to the normal, so your hand sketch of the t distribution is going to look just like your hand sketch of the normal. That's fine. Then we're going to figure out the critical value. You can use a table, calculators, computer. I'm going to show you with a table. Then we're going to estimate our standard error. And so notice this time, instead of putting the population standard deviation in the numerator, we're going to put the sample standard deviation because that's the only standard deviation we actually know. And so we're going to use that t as a multiplier the same way we used z. And then that's going to create our margin of error, which we're going to add and subtract from our point estimate. So this looks very similar to what would happen if we actually knew the population standard deviation. Okay, so this should look familiar to you. Let's do an example. Let's just suppose that we have a sample of 40 American college students, and they were surveyed about the number of hours outside of class that they spend on their studying. They came up with a mean weekly study time of 11.9 hours, so that is going to be our X bar. And their standard deviation of the weekly study time was 9.6 hours. So this is a standard deviation not for the population, but for the sample of 40. Okay, and what is my n? My n is 40. Okay, and so we are being asked to construct the 90% and the 95% confidence intervals. Okay, so the first thing we want to do is ask ourselves, are the assumptions met? Okay, so we need to have one of two things here. So, and let me make this an either here. The study time to be normally distributed. And so sometimes in your problem it'll say that you can assume that. Or our second option is that n is at least 30. So does it say anywhere that we can assume that the study time is normally distributed? No, it does not say that. However, we do have n is equal to 30. Okay, I'm going to put a question mark by each of these, and I'm going to say a big old yes for this one, and so that means we're good to go. Okay, and so if neither of those were met, as far as our class goes, you would need to put a note that says that we can't do this using the t-distribution, and then you would have to take a more advanced class and learn some more advanced statistical techniques that you can do on small samples. And so actually carrying that out is beyond the scope of this class, but deciding whether we can use our algorithm or not is definitely something you need to be able to do. Okay. So what else do we need to figure out? We also need the degrees of freedom. Okay, so remember this is our df, and that is going to be n minus 1, and so that is going to be what? 40 minus 1, so 39, right? Okay. So what do we need to find here? Our standard error of the mean, or just our standard error. And I always like to label this with the words standard error, and that will help me when we get to a more advanced section. We have different formulas for the standard error, but we're still always finding the standard error as the first thing. Okay, so this is going to be the standard deviation of all the x bars, and so that it's going to be the population standard deviation over the square root of n, except we don't know that. And so we are going to put a little approximately equal, and we're going to put the s up there instead. That's the sample standard deviation. Okay. And so for us, what does that give us? This gives us 9.6 divided by the square root of 40, which is about 1.518 hours. Okay, so that's our standard error. Now let's draw a little picture of our t-distribution. Okay, so when I draw my picture, it's just a sketch, so my t-distributions look just like my normal distributions. Just try to make it kind of bell-shaped. Do the best you can. It's not going to be perfect, and that's okay. Okay, so we need to come back here. Now, what confidence level do we want? We want 90% and 95%. So let's just call this one part A, and then this one part B, okay? So the first thing we want to find is the 90% confidence level. I'll move in my picture. Okay. So for part A, we want to find the 90% confidence interval. Okay, so here's my picture. So my alpha is going to be what? My alpha is going to be 1 minus 0.9, right? Which is going to be what? 0.10. Okay, and so then what are we going to do with that? We are going to put half of it into each tail. Okay, so alpha over 2 is going to go here. So that's 0.10 over 2, which is what? 0.05. And then same thing over here. My alpha over 2 is equal to 0.05. So we get half in each tail. Okay, and so now what values are these on my x-axis? This is going to be t 0.05 subscript. And that's going to be a positive number, and so negative t 0.05 here. Those are going to be the critical values. The critical values are where the color changes. Okay, so we need to figure out what our critical value is. So I'm going to show you how to do it with a table. We're going to call this the t-table. Okay, so let's go to our t-table to find the critical value. So I'm going to go over here to where my tables are. And I'm going to scroll down. Here I've saved my t-table. So this is also in your book, something similar to this. Okay, so what we're looking for here is we want to figure out the area in the right table. So in our case, that means that we want this area over here. You can see in this picture. So this is the shaded area that we want. And so that T alpha is going to move left or right depending on what our alpha is. Okay, so we want to look for that area. So that's going to depend on our confidence interval and our degrees of freedom. So those are the two factors that are going to affect our critical value, the confidence level and the degrees of freedom. So for us, what is our degrees of freedom? Our degrees of freedom are 39. And what is the area in my right table? Let me look at my picture again. Area in my right tail is 0.05. And my degrees of freedom, n minus 1, is 39. All right, so back to the table. Okay, so area equals 0.05 is going to be right here. And so I'm going to have to do a little scrolling here, so we're going to keep track. So that is the fourth column in. So I'm going to come down here to 39. And it'd be good if you followed this in your table. If you have a printed table, it's way easier, I promise you. Okay, and so it turns out this 1.685 is the one that we want. So that's degrees of freedom equals 39 down the left side, and an area of 0.05 across the top. Okay, so let's remember that number, 1.685. I'm going to just undo this so that I don't leave my table marked up for the next problem. And then we are going to come back to where we belong. Okay. So basically from our table, for degrees of freedom equals 39, and right tail area, which remember is going to be alpha over 2, equals 0.05. So those are the things we're going to look up in the tail. Then my critical value is t, we're going to still call it t.05, is going to be 1.685. That is our multiplier. So we're going to multiply that by our standard error and then add and subtract it from our sample mean. Okay, so basically what you do is you're going to take your sample mean and then you're going to do plus or minus your multiplier. So z or t, in our case t, multiplied by your standard error. So this is going to be our general pattern for all our confidence intervals. Even when we move to later chapters and we do confidence intervals for a proportion or a difference between two means or a difference between two proportions or if standard deviation, whatever we're doing is going to be laid out like this. Except over here on the sample mean, this is going to be your point estimate of whatever. So in our case, it's a sample mean, or it would be the point estimate of your parameter. So that's basically what you're looking at there. So that's just our overall pattern. It's always going to be laid out that way. So for us, now what we're going to do is we're going to have our, let's do the lower bound first. So it's going to be x bar minus my t, that's my multiplier, times my standard error, which is going to be my s over my square root of n, which we already calculated. And so this gives me what? So my x bar was, let's just go look real quick, 11.9 hours. My standard error was what? 1.518, and we've got our multiplier from our table, 1.685. So 11.9 minus 1.685 multiplied by 518. Okay. And so when you work this out, this is going to be 9.342. And so then let's do the upper bound the same way, except this time we're going to add. X bar plus my t.05 multiplied by my standard error okay, and so then that gives me 11.9 plus 1.685. If you have a calculator that saves your past operation, you may be able to use your shift or your second function key and then your entry key to pull up your last calculation, and then you can just simply type over the minus with a plus. It'll save you some keystrokes. And so this one turns out to be 14.458. Okay, and so what that means is that our 90% confidence interval is, I'm going to write this in interval notation, so always make sure the small boundary comes first, the lower bound comes first. So there is our confidence interval for the 90% confidence level. Now, we could put this on a number line, and the x bar, 11.9, is going to be exactly halfway in between those two. So ask yourself, if we do the 95% confidence interval, will that be wider or narrower? We should already know. We don't need any calculations to figure that out. We should already know whether it's wider or narrower. What you want to remember is that there's a trade-off between certainty and precision. So if you want to be more certain, you're going to lose precision. You won't be able to estimate as closely. Okay, so let's keep that in mind as we go on. If you want to estimate very closely, that's great, but you're going to lose some confidence. You're not going to be as sure of capturing the population parameter. Okay, so let's now try to figure out the 95% confidence interval. I'm going to call this part B. And we've actually done a lot of the work for it already. So we don't have to start over from the beginning. Our standard error hasn't changed. Our sample mean hasn't changed. Okay, so in other words, my standard error is still S over the square root of n, which was our 9.6 over the square root of 40, which is our 1.518. And so you could just copy that from where you already had it. My x bar, my sample mean, is still 11.9. My n is still 40. And so then my degrees of freedom is still what? 39, right? Okay, so now 95% confidence interval tells me what about my alpha? So that means my confidence level is 95%. And so that leads to an alpha of what? Alpha is equal to 0.05, right? Okay, so our confidence interval gets me my alpha. And so what we're going to do is we're going to put alpha over 2 in each tail. So 0.05 over 2, so that's going to be 0.025 in each tail. So if we do our little sketch, here's my sketch. So my alpha over 2 is 0.025 here and here. And so then, what are we going to call this place where the color changes? That's our critical value. It's going to be T 0.025 because 0.025 is my right tail area, and then this is going to be the negative of that. Okay, so now what we need to do is we just need to go to our table. And so we're going to use my degrees of freedom is equal to 39, and my right tail area is equal to 0.025. And so that's going to give us a t value. So t.025 equals, okay, let's go to our table. So this time we're going to look across the top. Hang on, let me scroll down to it. Okay, so we want to find 0.025 across the top because that's our right tail area. So if you look, that is going to be 1, 2, 3, 4, 5. That's the 5th column over. If you had a whole sheet of paper and didn't have to do all this scrolling, you could just follow your finger straight down. And so then I'm going to go down to 39. Fifth one over, 1, 2, 3, 4, 5. Gives me what? 2.023. That's the one that we want. Now, something to point out about this table before we go back. This worked fine for this, but if you look, at least our particular table, once you get past 40, it starts, then it jumps all the way to 50, then to 60, and then all the way to 80, and then 100, 200. So what happens if you, say, had a degrees of freedom of 47? So it's not in the table. It will be in some tables. It depends on how detailed your table is. So, but if you're using a table, then the general rule of thumb is if your table doesn't include it, just use the closest one, and that's going to be close enough. Once we get to real big degrees of freedom, it starts to look so much like the normal distribution that it doesn't really matter. Subtracting that 1 from the end, it makes a big difference if you have a small group, but it doesn't make a big difference if you have a large group. Okay, so just kind of keep that in mind. We're estimating after all. Everything here is an estimate. All right, so that I'm going to clear my table again. That 2.023 is the one that we want. All right, so I'm going to go back. I'm going to remember that. So 2.023. Okay, that's my critical value. And so I do my lower bound. X bar minus my critical value times my standard error. Okay, and so then that is going to give me 11.09 minus 2.023 multiplied by, this is the same standard error that we had before. So again, if you wanted to use that little calculator trick, if you had a either a graphing calculator or a scientific calculator that has a way to go back and do second function and then entering it pulls back your previous one, you could just take your previous critical value and type that 2.023 over it. Okay, so this is going to give me 8.829. And then my upper bound, same thing. This time we're going to add. And hang on, I just found a little typo here. This should be 11.9, not 11.09. In case you can't tell, I had this worked out ahead of time and wasn't just doing it with my calculator. So I copied it wrong. There we go. And so then this should give me 14.971. And so what that means is that my 95% confidence interval is 8.829 to 14.971. Okay, so let's go back and do a quick comparison with the 90% confidence interval. Remember the trade-off between certainty and precision? So this one is more certain. 95% is more confident than 90%. Therefore, it's going to be less precise. It's going to be a wider confidence interval. And so look, sure enough, this is going to be closer in toward the sample mean. The one we just did down below is going to be further out, lower on the low end, higher on the high end. Okay, so hopefully this example helped you figure out how to calculate confidence intervals when you do not already know the population standard deviation, and so you have to use the sample standard deviation as an estimate for that, and then we end up having to use the t-table instead of the z-scores. So that's all for now, and I hope that helped.